So we are proceeding with the examples of nonlinear systems, where in this case we are trying to determine the outcome of the competition modeled by this system here. So we are assuming that we have species X, species Y, and they're competing for a resource, and their competition leads to this system here. So basically, this system is nonlinear as usual, and we need to find the equilibrium points first. So how do we find the equilibrium points? We set the right hand side of each equation to 0 and solve for x and y simultaneously. So that's what we are going to do. So what are the equilibrium points? So it's x into 100 minus 4x minus y is equal to 0, and y into 60 minus x minus 2y is equal to 0. In class, we talked about how we can solve these. So we have different combinations. The first case is when you consider x is equal to 0 and y is equal to 0. Basically, we are saying if we consider x is equal to 0, it's enough to send the first equation to 0. If you also consider y is equal to 0 here, it's enough to send the second equation equal to 0. And which means we have an equilibrium point, x is equal to 0, y is equal to 0, satisfying the definition of an equilibrium point. Then the second case, we are saying x is equal to 0, but y is not equal to 0. So now if we take x is equal to 0 here, the first equation is satisfied, it's going to be 0. But if y is not equal to 0, which means we are forced to take the other one equal to 0. So this means 60 minus x minus 2y is equal to 0. But x is already what? Equal to 0, right? So x is already equal to 0 by this assumption here. So we put a 0 there. This implies that y is actually equal to 30. So in this case, we have another equilibrium point where x is equal to 0 and y is equal to 30. And if you plug these values into the equilibrium, into the system of equations here, you get that is satisfied. So it's an equilibrium point. So the case 3 case 3, we are then saying x now may not be 0, but allow y to be equal to 0. And if you do that, if x is not equal to 0 here, then you are forced to take the expression in the bracket and set it to 0. So it means 100 minus 4x minus y is equal to 0. But remember, minus y is equal to 0, but remember y here, remember y is taken to be equal to 0. So y is already 0 here. Y is 0. So this leads to x is equals to 25. So we now have an equilibrium point 25, 0. Now the fourth case, then assume x is not equal to 0 and y is not equal to 0. So the first equation, if x is not equal to 0, you are forced to take this one to be equal to 0. And the second one, if y is not equal to 0, you are forced to take this one as equal to 0. So in this case, you now have 60 minus x minus 2y is equal to 0. That's true. So then 100 minus 4x minus y is equal to 0. 100 minus 4x minus y equals 0. And now you play with your algebra here of solving equations, simultaneous equations. So the first one will definitely be, if you want, you can eliminate x here. Just multiply the second one by, by the first one by 4, 760 times 4, that's 214 minus 4x here. Uh, by subtract the bottom one from the green one. And if you do that, you then get 1. 240 minus 100, it's 140. And then minus 4x minus 4x, that's 0. Minus 8y minus y, that's minus 7y is equal to 0, which means y is equals to 140 over 7, which is 20. So if y is 20, if we go to the first blue one here, then we have 60 minus x minus 40 minus 40 is equals to what? Minus 40 is equals to 0. So then it also means that x is equals to 20. So we now have 20. So we can see that maybe let's list them. We have this one, we have 25 people, 0, 30. So basically we are saying here is x is y equals 0. This is more like both of them are not there. And then here you can see x is not present, but y is present. So here y is what? Dominant. And then here x is dominant. So x is excluded. Exclusion of x, and then y is excluded. But here both of them are there, so here we have got coexistence. So we can easily say there is coexistence here. Both are present. Now, what determines the, the question was to determine the outcome. So we then want to check which of these is stable. Okay, under what conditions? All right, so we then now want to find the Jacobian. Find the Jacobian stability analysis now. The stability analysis will determine the outcome. Stability analysis. So we have to find the Jacobian. So we now know how to find the Jacobian. So the other one would definitely give us, so we have, let's see, and the first equation is 100 minus 4x is x into 100 minus 4x minus y. I'm just, for the sake of making it much more clear, y into 60 minus x minus 2y, I think. Let me cross check. Yes, so I will then just expand them. 100x minus 4x squared minus xy. Here is 60y minus xy minus 2y squared. So we want to then find the Jacobian. So differentiating the first one with respect to x, I get 100 minus 8x minus y. That's what I'm going to get. Differentiating the first one also with respect to y, I get minus x. The second one with respect to x, I get minus y. The second one with respect to y, I get 60 minus x minus 4y. Okay, so there is our Jacobian. So we want now to check the stability of the extinction equilibrium. So this will give us 100, 0, 0, 60. And the eigenvalues are easy. 100, which is greater than 0. The other one is 60, which is greater than 0. So the 0, equilibrium is unstable. So basically we are saying extinction is not possible here. So extinction is not possible because no solution will go to this equilibrium point. Okay. That's right. Then let me go to the next one. So let's deal with 25, 0. Jacobian evaluated at 25, 0. Then this one will give us what? X is 25, 8 9 times 24, that's minus 100 here. 8 times 25, that's 200, 100 minus 200 minus 100. Then we have minus 100 minus 25 here. Right, so here is 0. Then 60 minus 25. That's what? 35. Okay, so here again, we have lambda 1 is equals to minus 100, is less than 0, but lambda 2 is equals to 35, which is greater than 0. So because one of the eigenvalues is greater than 0, this is a saddle point. But the saddle point is unstable. So 0, 0 is 25, 0 is a saddle point. The saddle point, and therefore stable. Stable. So which means it's impossible for species X to exclude the species Y. That's the outcome there. Then let's do the other one. J at J at 030. 030 is equal to, let's see. So X is 0, then 100 minus 30, that's 70. Then we have a 0 there, we have minus 30 here. And then we have 60 minus 30 times 30 times 4 minus 120. And again here, lambda 1, the eigenvalues here are easy, but naturally you should find is 70 which is greater than 0, and lambda 2 is minus 120, which is less than 0 again. 0, 30 is a saddle point and unstable, and therefore unstable. Yeah. So then the 3 are stable, so 1 should be stable. We can't have all of them unstable. So let's look at the equilibrium point 2020. What is the outcome? So let's put 2020 there. That's 100 minus 160. That's minus 60 minus 20 minus 1 minus 80. Okay. I hope I'm calculating it the right way. Then I have minus 20 here. I have minus 20 here. Then I have 60 minus 20, 40, 40 minus 80. That's minus 40. So I have minus 40 here. Now, in this case, I just want to use the trace and determinant. The trace here of J is equals to minus 40 minus 80, which is 120, which is less than 0. I am happy. What about the determinant of J in this case? That would be 40 times 80, right, minus 20 times 20. Surely 40 times 80 is greater than 0 here. It's greater than 20 times 20. So then this is greater than 0. So since the trace and the is less than 0 and the determinant is greater than 0, then the equilibrium 2020 locally asymptotically stable, locally asymptotically stable. All right, stable. So now what is the outcome of the competition? So the outcome of the competition says one, it's not possible to have extinction of both species. But that's not really what matters. It's usually on the question of is there a possibility for coexistence or not. So both, since the coexistent equilibrium is stable, locally asymptotically stable, so both X and Y species coexist. There is coexistence. That's the outcome.